Assalamualaikum. Good day, sir. First of all, I want to introduce myself. My name is Umina Bila binti Isa. I am FYP2 student under supervision of Dr. Idris Saad. I am here today to present about utilizing waste cooking oil as fuel for CI engine, optimize the number of fin type heat recovery device to preheat the biodiesel through simulation. This is an overview agenda of the presentation. I will start to present with introduce of this project, followed by project methodology, result and discussion, and I will end this presentation with conclusion and recommendation. So for the first section, which is introduction, I will cover the project background, problem statement, objective, scope and limitation. Let's just proceed with the next slide. So for the background study of this project, with the increasing of the industrial sector, the energy demand is also increased. The global warming effects, fossil fuel diminution reserve, and higher petroleum prices are the main issues driving global interest in developing alternative biofuel that are renewable, biodegradable, and sustainable. So to overcome the address issue, several research studies have identified that biofuels such as biodiesel have potential as an alternative fuel. So vegetable oils are one of the attractive and promising alternative for diesel fuel, as they can be manufactured locally and environmental friendly. But virgin vegetable oils are pricey and also preferable to use as a food. Thus, the usage of waste cooking oil could offer more benefits. However, waste cooking oil cannot be used directly in diesel engine because the fuel properties can lead to engine deposits, piston sticking, and injector choking. To overcome these problems, the most popular and commercially used technology for biodiesel production is transfer esterification method to use to optimize these undesirable results. Unfortunately, even after biodiesel going through transfer esterification method, the fuel properties of biodiesel such as density and viscosity are quite higher than conventional diesel fuel that can decrease CI engine performance. So on the other hand, another major problem that associated is less than 30% of heat energy provided by burning fuel is converted into usable mechanical power, and the rest is expelled to the atmosphere as waste. So researchers inspired to use waste to recycle heat from waste source in engine, which is not only decrease fossil fuel demand but also lower greenhouse gases and help save energy. Thus, a lot of research is done to minimize energy loss by using waste heat recovery system at exhaust gas that contain high in temperature. Therefore, to further improve the performance in the CI engine and in reducing greenhouse gases, this project is aimed to focus on preheat biodiesel by recovery of waste heat energy from diesel engine exhaust gas by using waste heat recovery device. The fin type waste heat recovery device will be used and modified in the exhaust manifold to preheat the biodiesel fuel. For the problem statement, biodiesel contain high density and viscosity that lead to fuel flow ignition problems and high emission in unmodified CI engine due to the difficulty in atomization and vaporization. So on the other hand, it has been confirmed that more than 30% of fuel energy is wasted from the exhaust, resulting in entropy rise and serious environmental pollution that is required to utilize waste heat into useful works. Hence, regard to the problem, a simulation test of fin type heat recovery device will be tested with a different number of fin to analyze the most efficient heat transfer rate model to preheat the biodiesel. Okay, for the main objective is to absorb the amount of waste heat from the exhaust to preheat biodiesel before entering the CI engine to increase the CI engine performance and decrease exhaust emission. The detailed objective is to evaluate the rate of heat transfer of the waste heat recovery device to analyze the optimum number of fin that can absorb the maximum amount of heat to preheat the biodiesel. For the project scope will focus on heat transfer rate of the fin type heat recovery device. The heat recovery device will be used to absorb heat that produced by exhaust to preheat the biodiesel before entering the CI engine. A 6 model with the same size and evenly arrangement with a different number of fins will be tested using ANSYS 6.0 version. So the result will be compared which model obtained the most efficient heat transfer rate. So for the limitation for this project is this project only covers simulation result of heat transfer rate by using ANSYS 16.0 software. For the next session is project methodology. The concept of this project is a double pipe counterflow heat exchanger. The principle of counterflow heat exchanger is used to determine the heat transfer rate between cold fluid and hot fluid, which is biodiesel and carbon dioxide. So the rate of heat transfer is determined via conduction of between two pipes, which is exhaust and sleeve. In this schematic diagram, the pink pipe shows the hot gas flow and the grey pipe shows the counterflow of the cold fluid. This is the flow chart of methodology for ANSYS, which I will explain more detail in the next slide. In this study, the type of workbench used is fluid flow fluent. As for this simulation, there are 5 stages to achieve the result, which is first stage is geometry, design modular, second mesh, and then setup, solution and result, which is mean CFD post. The figures shows this is the overview of the ANSYS Fluent Workbench Monitor. So for this study, the geometry section we used to design the model using design modular. There are 2 types of model, which is first base model and second is fin type model. The fin type model will be sketched with 6 different numbers of fin. First, for the base model, at the exhaust pipe, the inner radius is set to 16.0 mm and for the outer radius is 16.5 mm. The dimension of the model exhaust manifold is based on the CI engine model at the Automotive Laboratory Faculty of Mechanical Engineering, UITM. For the sleeve, the inner radius is 26.5 mm and the outer radius is 27.0 mm. Both exhaust and sleeve have 0.5 thickness. In order to build the model, the inner pipe and outer pipe has been extruded with the length of 70 mm and 48 mm. Next, I use fill tool to add hot gas and cold fluid for the counterflow heat transfer. Then before proceed to the mesh stage, all the bodies need to form in a one part as to be able all the body is matched. Okay, for the fin type model, the design of fin was added in cold fluid region that attached at exhaust manifold with dimension and width with the fin is 0.5 mm, height 7 mm. The depth of the fin is same with the sleeve, which is 48 mm. The dimension is fixed to all fin type model. Okay, to increase the number of fin, the pattern tool is used in the design modular to sketch. The angle for all model is set to evenly spaced. For the mesh step, the base model is first used to find mesh optimization to get the optimum point of the mesh. And the mesh process include phase meshing, inflation, edge sizing, multi-zone with prism and hexa method. After mesh optimization is obtained, the maximum phase size number is used for the fin type model. Here was the mesh setting at optimum point for fin type and detail mesh setting at sizing selection. For setup and solution, in the setup step, the parameter of waste heat recovery device is set. The parameter includes viscous model, energy use is set as shown in the left figure. Okay, and then the material and cell condition is set accordingly, as the cold fluid and is diesel, hot fluid carbon dioxide, exhaust is set to steel, and sleeve is set to as a copper material. Okay, next, the parameter used for the simulation result is set as shown in the table, where the temperature and mass flow inlet for both hot and cold fluid is fixed. After all the parameter is setting up for the solution step, the solution is initialized at standard method and compute from all zone. Lastly, the calculation is run at 200 iteration and the result of the temperature difference between hot and cold are obtained as shown in the figure. So for the result, the heat transfer simulation is shown was visualized using CFD post simulation. The simulation made it possible to visualize heat transfer, gradient of temperature, streamline volume rendering, vector of airflow, and etc. So this is the result for base and fin type CFD post. This is the continuous CFD for different number of fins. For the next section is result and discussion. The figures shows the volume of temperature exchange for the model 1 fin type WHRD, which is waste heat recovery device. We can see the different color is indicate the fluid changing temperature at the hot gas inlet. The dark red show the temperature of the gas in high compared to the hot gas outlet that turn to lighter red with some orange color. The simulation result is shows that the cold region, which is BIODIESEL, is slowly changing the temperature from cold temperature to higher temperature, and vice versa with the hot region, which is hot gas. So at the right hand side, we can see the table. It shows the result obtained for the from the simulation of base model and 6 fin type waste heat recovery device model. Basically, the table from the previous slide shows that for every model, the temperature cool outlet is increased and the temperature of the hot outlet is decreased. The fuel outlet temperature for base is increased with 15.46 Kelvin, while for the one fin type waste heat recovery device, the outlet temperature is increased up to 26.97 Kelvin. Theoretically, as increase the number of fins, the temperature cool outlet should be increased too. As the simulation result shows that as increasing the number of fin that run at 200 iteration, the temperature outlet is slowly decreasing compared to one fin waste heat recovery device. This is might due to several factors. So for the performance CI engine and exhaust emissions, as obtained result, the temperature outlet of the biodiesel is increased and lead to decreasing viscosity and density, which means it will increase the performance of the CI engine. And the temperature outlook for the exhaust is decreased, resulted decreasing in greenhouse gas. For the last section is conclusion and recommendation. As for the conclusion, the major concern of this study is to decrease the density and viscosity of the biodiesel through the simulation of heat transfer rate using 6 model fin type waste heat recovery device was done. With the increasing temperature of the biodiesel, the few properties such as density and viscosity will decrease and can lead to higher efficiency of CI engine performance. So from my project, the higher temperature cool outlet that I obtained is at model 1 fin type waste heat recovery device with 350.11608 Kelvin. For a better and more accurate result, this study is recommended to be taken under real condition of CI engine, or increase fin contact surface area with the exhaust, and or change exhaust material type from steel to copper for a better and for a more heat transfer rate efficiency, and increase the smoothness and fine meshing. That's all for the presentation of my final year project. Thank you for your time. If you have any question, you can contact me through the contact info provided. Thank you.